Thank you. I've always been interested in network communication, and who is not fascinated by the epic story of Lord of the Rings. So I thought maybe why not combine these two interests and try to explain how to use gRPC while fighting Mordor. So my name is Per-Magnus Holtmo, working as a consultant, been playing with C++ for quite some time. Currently working for Net Insight, pretty deep into low-level network communication. So let's get going. This microservice architecture you see it everywhere now. It might have started in the cloud systems and then in web-based systems, but now we see them all around, even in very small embedded systems. So you have one service serves one purpose. So we need a robust, efficient way to communicate between the services. It should be efficient and easy to work with, of course. And there are several options out there. The first you might think of is REST APIs, sending JSON strings all around. It's nice, it's human readable, it's easy to understand, but it's maybe not the most efficient way to parse and stream these large chunks of strings. They need to be careful with spelling as well. Other options might be, MQTT is popular for sending small messages. You can use standards at RabbitMQ, StereoMQ, sending whatever data you want to, Apache Kafka, and so on. You can implement your own systems with raw sockets. Some will need broker processes. Yeah, several options. Or you can use gRPC. It was made by Google and turned open source in 2015. So it's pretty new. It's an RPC framework supporting most popular programming languages. It's using Google protocol buffers for message serialization and interface definitions, and using HTTP2 as a transport layer. Of course, you might think that G stands for Google, right?
Yes.
Any other suggestions? Does anyone know what G stands for? No GNU. No generic.
General.
No general.
Gondor.
Good guess. We all would like it, but no, it's actually different words for every release. So someone thinks they were funny. I guess it was Google in the beginning, but it changed. Okay, let's design a simple game with Lord of the Rings. I'm going to show you how to make this a server. Going to be a lot of code today. I'm going to try to explain how to hands-on use gRPC with C++. So we're going to make a server application exposing this gRPC interface and a few client applications. We're looking at the service interface, we're separating that into a specific library, so it can be used on both client and server sides. Look at both synchronous and asynchronous communication schemas, and hopefully look at some message streaming as well. If we start with the interface, as I mentioned, it's using Google protocol buffers to defining the messages, and that's defining protofiles. We use that to generate C++ code that we then can put in a library for use on where we need it. So let's go into these details. Most of you have seen protobuffer files before. It's pretty common message format. It's in the .proto files. And we start to define the package. The package will give you the namespace so you generate the code later on. So it's good to know. Since my service is going to have the loader as the main namespace, I name a package loader.proto, so proto will be the sub-namespace or the protocol. So we define the messages that are going to send to the server and from the server. Of course, we want to know the population of Mordor. So we have this Mordor population message sent from the server. We can know a number of orcs, trolls, Nazguls, and is Sauron still alive. You know that orcs reproduce like crazy, so we need to be 64-bit to handle a number of orcs. But most common types are supported. And then we're going to strike an attack to Mordor. We use a weapon, so we send a weapon message, defining a name and the power we are able to give it to it. And as a result, we'll get an attack result back. Number of orcs, trolls, and Nazguls have been killed. So this is how you define messages for the protocol. It can go either way. And then we use the proto-compiler to generate some C++ code from this. Give it just an include path and tell it when we want CPP out in this folder. And the input is a protocol file. That will generate header file and some implementation file. And if you look at the example how this is used then, we create our weapon instance. We use the setter methods to set properties. This can then be serialized into a string in this case, or data buffer. There are several options. Strings are normally used for byte array containers in protobuffer. Then we can deserialize it on the receiving side, just create an instance of your type, parse from string if you have the data, and just use the getters. So this is the basic for message handling with protobuffers. Then gRPC makes additions to this protobuffer files. They have the service keyword. You can use that to define your service, telling what actually functions you're exposing. So we have a loader service here, simple one with 3 methods. All methods take one argument in, one message in, and returns another message. So always one-to-one. So the first one, I want to ask for Mordor population. I don't have no arguments to send, so using the standard empty message. And then it returns a Mordor population message. The other one, kill orcs. We provide the weapon we're going to use when we send the weapon message to the server. And back we're going to get the attack result. If you want to send more messages or receive more messages, you can just combine them. Message can contain any number of sub-messages and array of messages. So you can make this as huge as you want to, but it's just one message as in argument and one return. Those two first, one I call it unary functions, just like a request reply. The third one is example for, then you can send streams. You can send a stream of messages to the server and back, or both ways. So the third one has a stream game status as a return type, meaning that the server can then return 0 or any number of messages until the server stops sending it. So that's the streaming. We're going to talk about this a bit later, but we start with the simple unary calls. Then we run proto-compiler again on this file, telling it we want the gRPC output, and telling it what plugin to use for that one, CPP plugin. And that's going to generate 2 other files, header file and implementation file for the service itself. And in some way, here I put it in a library. I made a simple CMake function. It's don't go into details, but just loop over the proto files, generates header and implementation files, build a library, expose a header folder for the target made. So just details, but then you can add helper functions or queens functions. You can give it a version for this, but keeping the interface in specific library is very good, because both the client side and the server side can use the same library, and you can ask, are we using the same version of this protocol, and so on. Okay, let's start to look at how to make a server. We have the server and service concepts. The server is running, hosting a number of services. We define the service in the proto file, holding a number of RPC functions. So the service we must inherit from a generated class for service. Then we create a server to expose this service on a given port, IP port. So we're going to start the server, let it run until we tell it to stop. So if we continue and look at the details, how to set up this simplest service. We include the generator header file, and we must inherit from this basic service class. And then I must override the functions to use. So here we override Mordor population, and it must look like this. The arguments are context, request, response. Always of these three types would be over and over again. Context, request, response. So it's on the server side. We will be called with these three objects, and we're returning a status in this case. This is an synchronous call, so we're going to handle the request and return a status. The gRPC status is just have an error code and an error message. So looking at the implementation, very simple. We don't need to care about the context right now, and the in argument is just empty. So we get the response, fill it with data, and return a status code. So that's all you need. But this is called from a gRPC thread, so it can be called anytime. So of course you have to think, you need to get the data from your game engine, from your main thread. You need to think about guarding your state, of course. I don't mention it here, but of course you need some way to get the data safely. But you must set it directly and return a status code. Then we need to host this service in a server type. This is generic class, just holding at the bottom you see this gRPC server. And it's going to be run forever, so we're going to keep it alive. So we need a thread to hold it in. So this is just a container for the thread running the gRPC server. So we have the run function. So just looking at the thread function, looks like this. We're giving it a service that we're going to host, and a URL IP import that we're going to listen to. So create a server builder, set the listening port, well, IP and port. And here we don't care about credentials, we just use the standard insecure credentials. Then we register the service. We call the build and start. We're going to return a unique pointer for this service. Then we call wait. The wait is the blocking call that will, as long as the gRPC is running, we're going to block on the wait call. So that's why we need to hold this in a separate thread. And to shut down later, we need to, from another thread, call the shutdown function, as you see below. So when we're going down, we're calling shutdown, waiting for the thread to exit, and then we're fine. I can point out here that this wait function will not release until all gRPC outstanding calls are handled and closed cleanly. So the most tricky part with gRPC is actually to turn it off. So you have to be careful when turning off any outstanding calls, clean up, then we can shut it down. But we'll see some examples of that later. Okay, go to the client side, how to make a client. The concepts here are, you see to the left, you have the server hosting the service. Then we're going to create this generic channel. Channel is the object that transport object, handling messages, sending over HTTP2. But then we're going to generate a stub. The stub resembles a service, of course. The stub has the RPC interface. So a client uses a stub. The stub is generated from the service we're exposing. So we're calling functions on the stub objects on the client side, transfer to the server side. So for this, we're creating a generic client, holding this client to stub that we need. And then we'll make a specialized client specific for our purpose. So looking at the generic client helper, this gRPC client, this is all we need. At the private part, you see we have this gRPC channel, as well as a service stub that's service specific. And in constructor, we create the channel on the provided URL we're going to connect to. So we give it a server URL or port. So create a channel to this server, and then create a stub based on the template argument, the service.
Why does it need to be shared and not unique?
Very good question, since gRPC is unconsequent. These functions create channel returns a shared pointer, and the service new stub returns a unique pointer. So it is what it is. And then we have this one getter function, the stub. We just need the stub to be able to call our functions on it, so we return the stub. Then for our specific game client here, in the constructor we just take the IP port we're going to connect to, and then we'll make this. Okay, I want the population in Mordor. So make the population function. Here I picked to return a std optional because the call might fail, of course. You could return error code or whatever you want, exceptions, but here we return an optional. If you look at the function that we're going to implement, call, on the stub exposes this function at the top. More population takes a client context, request, response. So when we implement this synchronous function, population, we're creating on the stack just a context, request, response, and using a generic client here to get the stub. On the stub object, we're calling the function more population. That's a synchronous call. So it's going to fill the response object, and then we get the status. The status tells us if the call was successful or not. If it was, we can use a response. So pretty straightforward. And this client context we talked about, here you see I create a context, but I don't do anything with it, but it's also is needed. The server got the context, but didn't use it. But you have several options you can set on the context. For example, the client can set a deadline. So the call will be aborted if not returned within X number of seconds, millisecond. That must be in absolute time. Could be a duration, but it must be an absolute time. We can set the compression. There are a few options available as default. And we can set metadata. We can set key value pairs into the header that the server then can read from. So, and you can set credentials. You can cancel outstanding calls. There are keep alive options. You can wait for ready if the server is going up or down. So this whole context has a lot of features, but you might not need any of them. Another really cool feature actually is you can just enable reflection with a simple call. What that means is that there are a lot of command line tools. If you have the server running, you can query it. What are the services you expose? What are the function the first service expose? What are the arguments needed? You can even call functions. There's a gRPC curl, for example, but there are lots of tools that you can communicate with the server just from command line for testing. So good for testing, just easy to enable. Yeah, I can show you some short demo of what we got so far. Not that fancy, but still, if you start in the server, you start listening on the ports, and we can just see how now it works is growing. If you start this synchronous client, I can query for a population. We can kill some orcs, quite a few in one go, not that bad. And if you're waiting too long, select the population. We can let it goes pretty quickly here. If I'm not killing it fast enough. So, yeah, sorry. Sauron got us. If then the client is still open, if I try to make a call here, like ask population, no, fail to connect, of course. If we start the server again, and making a new call, still get fail to connect. One more second, here I got it. Might be annoying, but there's an inbuilt back-off timer here, so you should not be able to spawn the server with requests if a lot of client site requests connect at the same time. But you can change that. But otherwise, it's you can just turn on, close the server, start it again. It's pretty efficient throttling connection handling.
Why is it listening on 2 ports?
Because I have one synchronous and one asynchronous.
Jumping ahead.
Yes. So let's leave it like that. It will die by itself. But there's a problem. Very obvious one. You see, when I strike this attack, I'm frozen. I'm very vulnerable. I'm open for attack myself. So I must be able to, when I strike an attack, I must be able to run and hide, of course. So what do we need? Yeah, we need asynchronous message handling, of course. And it's interesting because when you read the documentation, you start with the basic synchronous examples, and then you go to the async. You just get tired. There's completion queues, and they are waiting and threading and polling and what's so not. So you just get bored when you see it. But there's actually a better callback interface. It's not hardly documented at all, but there is available source code examples in the gRPC repo. So they have examples for it, but they don't mention it. It's a bit newer, but it's still several years old. So we can look at how to make this asynchronous service instead. We just, for the service side, we need to inherit from another class. We pick the callback service. And then we need to implement, override a few functions. You see, they always take the context, request, response, as always. But now they return not a status, but a unit reactor. So we need to create an object and return that. And then we can later mark that object with, okay, now I'm done. Here we're going to use the boost ASU for event handling and threading and so on, just as an example. So we're taking that in the constructor. And if we're looking at implementation for the same kind of call, we get in the more population asynchronously. We get the context, request response. For this simple case, the unary calls, request reply, the context actually has a function to get the default reactor. Makes it very convenient. So we get this reactor object, but then I post that to the main thread using boost ASU, capturing and pointing to the reactor, and then return the reactor directly. So remember, this is called by a gRPC thread, so we must hand over to our main thread and return the reactor. So that's what we do. And then after a while, when the event is handled, we can safely use the callbacks for the game engine, get the population, set response properties, and then mark the reactor is finished. So then when we call finish, that's actually when the message will be turned over to the client side. So not much more code than a synchronous one, but so it's pretty easy to do in the server side. But still, there's another problem in this code related to the shutting down the service, because this function is called by the gRPC thread at any time. So, and what will it do? Yeah, it will push events to our main thread, post events. So let's say we're shutting down, we're turning off a lot of objects and going down, we're about to turn off gRPC, but suddenly this function is called by another thread, posting events to our main thread, initiating a new gRPC call. Then we want to stop gRPC from running, but it will never stop since it has this outstanding call. So in some way we need to stop handling accepting new calls from the gRPC. There are several ways to do it, but the simplest one is just to having this shutdown guard here. Just adding this. When we're shutting down, we're setting an atomic variable. And then we can see this is called from the gRPC thread. Get the default reactor. If you're shutting down, just call finish on it, put cancel. I don't care about your call anymore. That's safe. It's done in a separate gRPC thread. We can also check some input argument validation on the gRPC thread. Like the power should be between 0 and 1, for example. If not, we return an invalid argument with any message. So this is a bit about how you can do some error handling. But then if you find, we just post our main thread, let it be handled later on, return the reactor, and when the main thread is done, we can just mark it as finished. So that's a bit of an improvement. If you look at the client side, we're going to connect to the server, so we connect with an address and port. And looking at the killorgs function here, it's a void function now because we're going to send something in this way, the killorgs message with the weapon and power, and we create a kill handler, a callback. So we can just send our strike, run and hide, and wait until the handler is called with the result. We can check how good we did. So look at the implementation. I said the stub is generating all the RPC functions. There's a subtype in the stub, it's the async. So in the async instance, we can use these killorgs. Always takes the context request response. But now there's also a function, a callback function, that will be called when the actual call to the server side is returned. But if we look at this signature, it expects 3 pointers to 3 items, and some later point in time they will call this callback F. So sometime later they will read from and write to these 3 instances. So we need to keep those in memory until the F function's callback is called back. So it makes it a bit tricky. So I put that in a client state. So these are the 3 objects we need to keep alive for every single asynchronous call until it's returned. This might look a bit messy, but it's... So when we call in the killorgs, we're creating this shared state as a shared pointer. We're setting the properties for the message to go away, for the request. And then calling the killorgs on the async stub, providing address to the context request response, and then copying the state to Lambda here, so we keep it alive, the shared pointer, until this function here with the state is to call back. After a second or so, we get the return from the server side. But on a gRPC thread, of course, we still must hand over once more to our main thread, so we do a boost AC post in this case. And once we've done that, the state goes out of scope and the state is deleted. But in this case here, I copy the interest, the number of orcs killed from the response, just as an example. And then we got time, the handler is called from our main thread, providing the status of the call and response information. So not that complex actually, but if we go to message streaming, makes it a bit more complicated. But unary calls takes it pretty long. You can send large arrays of messages and you can get state and you can poll and do whatever you want, but it would be nice with some kind of event notification that would, let's say, changes to the server side or just getting up to date with information. So if we look at this example from the RPC definition, subscribe to status, it returns a stream of game status. And most examples for this is give me all restaurants in Södermalm. And the server just responds as fast as it can with a lot of messages. Give me all gas stations in Uppsala or whatever. But you can use just one message containing an array of messages if you want that, a dynamic array. It would be more interesting to have this kind of, you make a connection, you connect to the server, and the server sends message either regularly or state change. So that's, it can be used either way. But the subscription can be kept open as long as you want to. So we look at the method to override for this. Subscriber status, take the context and a request. But this one returns a write reactor. This means on the server side, we're going to create this write reactor in some way, return it. But then to that one, we're going to write our messages to the write reactor that will be streamed over to the client side. Then when we're done, we can just finish the reactor and delete it. So we need to create this kind of server write reactor. Here I'm going to show you, first we're going to make a message writer, which can just write one message to one client. Then we're going to wrap this around in a stream writer, just having a vector of message writers, so we can connect to any number of clients at the same time. And we'll make an update to the service. So this is a bit more complicated and boring code than the unary calls, but this is what you have to do as of today. So we need to override this server write reactor. And this is sending one message to one client. So of course we have this send message function, taking a message, a proto message. And we need to override three functions. On write done is called when one message is completely written to the client. On cancel is called when the client goes down, so connection goes down and we are disconnected. On done is called when the complete connection is done, we can delete everything, everyone is happy. But normally you send message, you get write done back. So look at some of the implementation. Could look like this. We're going to send a message. Here first check, are we sending a message currently? Is the last message not handled yet? Well, then we can't send another one. You could add a queue or whatever, but in this case, we just discard the next message. Or if you're going down, yeah, we don't start a new session. But in this case, I kept the message as an optional pointer. Optional, optional, not a pointer, of course. So when we're sending a copy, keep a copy of the message. When we start write, the start write function, gRPC call, we need to provide a pointer. You can read from this, and you write this to the client. And when done, we get the write done callback. So then we can reset it. So in some way, we need to know that this instance might be read from by the gRPC at any time until write done is called. So it's how we need to keep it in memory. Several ways to do it, but we need to know how long to keep it as well. But you can make queues or whatever. And also here, since send message is called from the application thread, we want to send message, but on write done is called by the gRPC thread. And we need some threading, of course, mutex or whatever you use to ensure your shared data is not used by two threads at the same time. This can be quite confusing in the beginning, what functions are called from what thread, but you need to think of it. Then we can make a stream writer that's going to hold a vector of these connections, all the clients. So we have a function create writer. Each client gets we call a create writer that can be returned to the client connection. And we send message. So what you need to do here is, in some way, for every client that connects, we create a new writer. I put a unique pointer in a vector and return it. Keep track of it for that is some unique ID in some way. And the send message, just a loop over all writers calling the send message. Here you can optimize depending on if you expect to have only one client. You can keep your message in one place. Or if you expect to have 100,000 clients, then maybe you don't want to copy the message to all objects. But still, if you send it to 100 clients, if you just have one instance to send, you need to wait till all clients are done until you can exchange that one. But depends on how you optimize, what your use cases are. You can optimize in various ways. But it's important to know how long should I keep this object in memory until gRPC is done with it. You will get unexpected crashes. That's how you learn. At least how I did. And the usage here, let's say in the async service, when we get a call, someone wants to subscribe to status, we just create a writer and return it. And then when we're going to send status to all connected clients, I will send status function from the application thread, create a proto message, set properties, and just to the writer send message, and that will send to all connected clients. So it's you don't have to care about how many clients you have. So that's pretty neat. Then we just need to read streams also from the client side. So the function we need to use here, it's also from the stub async. It's a subscribe to status function. Take the context request and a read reactor, another reactor type. So we need to create this new type, this read reactor, provide it to gRPC, and then we'll get events when there are messages to read. So we're creating a stream reader for the client side. We have to inherit from this client read reactor. Provide it some function callback that will be called when we get a new message. So greet the message handler. That will be called back when we have a new message on the incoming side. We have a start function, we're going to start the reading, but there are two functions that must be overridden. It's onRead done and onDone. And when a new message is read by gRPC, we get onRead done callback. And when everything is turned down, the connection has gone down, any error, we got onDone called with error. So it's pretty simple and easy to work with. And we keep the message as a member here. Since it's implemented like this, when we start reading, we need to start call. Start call sets up the communication between client and server for this call. And start read, we're providing it an instance to a variable that will be filled with from gRPC. So the message variable will be filled in. And after a while, we got onRead done. And then we know, okay, we have a new message to use. We can post the information to our message handler, call it from the main thread. Here you have a message. Then we call start read again with the same variable, but then it can be reused. So let's go over and over again. We get the message, onRead done, and we call start read. But to post it to our main thread to be handled. So let's think about what thread is calling which function. And finally, the usage from the client side. We need to create this reader. We're calling subscribe to status on the async stub, providing objects, and starting the reader. We're providing two callbacks here. One for the game status that will be called as soon as we get the message from the client side. We can do whatever we want with it. It's called from our main thread. And when the client connection goes down, we got a call from another callback. For example, then we can just delete the reader. Skipping a bit of details, but the important concepts are here. So that's what you had to be done to set up this kind of streaming connections. And we can show another demo here. Hopefully. If we start in the server again, we're starting async client. We can start another asynchronous client. If we subscribe, this one we're going to get calls every 1.5 seconds, I think. And we're going to call both. We can unsubscribe. We can kill some orcs. Subscribe again. And nothing fancy, but when the server goes down, you see both subscriptions exited with service shutdown. If I try to do anything here, no, I cannot connect. If I start the server again, I can directly start a subscription and kill some orcs, subscribe. So it doesn't matter if what order you start and stop anything. It's pretty convenient, the connection handling. It's works pretty nicely, actually. And you always get the event when you lose connection, if handling it the correct way. So, no nice GUIs to this game, but next time maybe.
Soon on Steam.
Yeah.
How do you win this game? You never won.
If I press really fast. Okay, that's about it with code. One question is very common with gRPC is, how do I know if I connected? How should I check if I connected? I must connect first. Well, there are options. You have this channel object. You can always ask the state of the channel. Are you ready? It's a call. You can check the state. Then you're connected. There are, as I mentioned, keep alive options. You can set it up. You can send pings in a certain intervals, and you can set the timeout. How long will you expect it? Allow it to wait for the pings. You can use your own messages to query state. Just if you get the response, you know you're connected. Or as I prefer, keep this subscription open. As soon as the connection goes down, you get an event, and you know you lost the connection. But still, if you know you're connected at time A, you have no idea if you're connected just afterwards. In network, you can lose connection anytime. So just keep your services running using systemd, Kubernetes, or whatever it means, and ensure to have proper error handling. Can sum up with some advantages, I think, about gRPC. I like the protocol definition with the protofiles. It's the contract between client and a server, and it's well typed. And you can generate code for various languages, Python, TypeScript, Golang, whatever. And protobuf is also efficient serialization. It makes the binary messages pretty small. And the gRPC is simple to use for the request supply. Not much code needed, but for the streaming it's a bit worse, boring code. But you have streaming support. And with HTTP2 you get a lot of TLS features and other things, and you have compression and what's not. So, but maybe not everything is good. It's a pretty complex and large code base. It's very large. For smaller projects, it must be a bit lot more features than you will ever need. It's not the best documented project either. Lots of documentation, but it's a bit hard to follow. And as you see in complex, streaming is a bit complex. You need to override quite a few classes. And just show the concept. You need to make good structure also, making it a bit more complex. Under the hood is a bit message intensive. It's meta messages back and forth when setting up connections and when the connection is done and so on. And yeah, it's very hard to shut down. You will be bit a few times. But And HTTP2 is supported by most browsers since, I don't know, 10 years. But still you cannot connect from browser to a gRPC server. There are features that probably will never be supported, unfortunately. So you need proxy server converting between HTTP 1 and 2 for it. Something not covered, yeah, we could have looked at other languages, clients, authentication, encryption. More details about shutting down handling and lifetime issues, but that's just boring code. So, yeah, finally. It's a big day for us smålänningar today. Yeah. Happy första torsdagen på mars. We should have marsipantårta och bärs. Yeah, that's it for me. Thank you very much. Source code and presentation is available if anyone wants to look at it. Any question? We're just tired after all the bloatware on the screen.
How much is the overhead if you were to write your own as low level as possible with mem copy of structs, etc.? How much overhead do you have?
Well, I could just kill geese. Yes. When you're making a simple call, get reply, you first the metadata from client to server, and then one back, and you get the message, and back, and afterwards another two. So a few more messages, and of course, mem copy of struct is very efficient compared to serializing the proto buffer. A lot of things involved here. So, but it depends where does actually the CPU cycles go, how much is actually network traffic. But yeah, a few factors more efficient to make it yourself. I would think. Yes?
Can gRPC handle different versions of the proto files?
Yes, they can. As you know, proto buffer has this support for versioning. If you're following it properly, it can handle additions to messages and some changes. It can, yeah. Yes?
So if it is not supporting HTTP2 protocol and I cannot use my browser as client, so what is the use case for this one? Like if I want to get a web application running, so how can I use this? Like what will be the use case? If as an end user I want to use a browser as a client.
As always, if you want a web interface to your C++ service, if you have that or whatever, you need a web backend. If you do that in Node.js and React, as is most common, you need that service to communicate with your gRPC. That's how I do it. I have my TypeScript server communicating with the C++ over gRPC. Or you can use a proxy server directly from the web browser. You can connect to the proxy, convert going over HTTP 1 to 2. So yeah. Yes?
As your experience, how much in your daily workplace, how much you can kind of isolate or separate the gRPC API layer from your like application and service? How much your like system get bounded to this gRPC implementation? For example, if you one day, for some reasons, if you just like realize that it's not enough or you need something else, how much is there like how much effort will it take to move?
How much as you want. You define the messages in a proto file. It's a prototype. You have this type. You can use that all around the application. You can use this weapon type all around if you want to, but then you can't change it. If you want to change to another Captain Proto, whatever, at the bottom. Or you can just make your own structs, convert into that, having your structs types at the interfaces. So you can make as many layers you want to, depending on overhead and how much time, how generic you want it to be. But you can hide everything at the bottom layer, of course, adding your layers on top on it.
With some overhead? Like
Yeah, always comes with some overhead. And copying of types, yeah.
Could you say something about the differences between the synchronous and the asynchronous API? Like, when would you choose one over the other? Would you only choose the asynchronous when you want like multiple messages in flight, or are there other benefits to it?
Yeah, since we talk about our network here, you don't really know about the delays and so on, and if something gets stuck somewhere. So if synchronous is actually a blocking call, your client side will be blocking. But if you just having two simple processes, maybe that's what you want to. Make a blocking call with deadline, just 1 second. I don't have anything else to do. Then it's fine with the blocking calls. But if you need to process user input, for example, you don't want the UI to be stuck.
Yeah.
So it depends on use case. Synchronous works in some cases. Just even if you need to process events at the same time. Yeah.
Is there, can you set limitation for the asynchronous API to, for example, limit the amount of threads?
For the server side, you have the thread pool running. You can handle several synchronous calls at the same time. The server must be responsive. On the client side, if you have one thread and one call, you can't do anything else than just one call at a time. Or if you have several threads, of course you can, but...
I mean, on server side, for example, set some limitations that doesn't, for example, accept more than 30 requests.
I'm pretty sure you can. There are a lot of features, but I haven't looked into that. Yes?
Is there existing or planned support for coroutine syntax for asynchronous interface?
There are discussions, but I don't think they are planning to do it in the near future. But I know in the forums, several people want this asynchronous API to be using coroutines. Yeah. Okay. Tack.